It's October 9th, 2022, and the gamma-ray burst, known as BOTE, brightest of all time, is flooding Earth. It was registered by space telescopes and observatories worldwide in just a few seconds, an unprecedented flood of high-energy radiation. The burst originated from a galaxy approximately 2.4 billion light-years away, meaning the light from this cosmic explosion had taken more than 2 billion years to reach us. What happened in that moment was incredible. The gamma radiation was so intense that it even affected the upper layers of Earth's atmosphere. The ionosphere, normally about 60 to 90 kilometers above the Earth's surface, was disturbed by the high-energy photons. Sensors around the world sounded the alarm, not out of danger, as the atmosphere reliably protected us, but because the instruments had never recorded such values before. But what exactly are gamma-ray bursts? How do they occur? And could they perhaps even lead to our extinction? Let's start with what exactly they are. Gamma-ray bursts are among the most energetic events in the known universe. In just a few seconds to minutes, they release more energy than our Sun will produce in its entire lifetime. There are two main types of gamma-ray bursts, which originate in different ways. Long gamma-ray bursts, longer than 2 seconds, occur when massive stars die, at least 20 to 30 times heavier than our Sun. When such a giant has exhausted its nuclear fuel, its core collapses in fractions of a second. This creates either a neutron star or, in the case of even more massive stars, a black hole. The collapse is so powerful that matter is ejected at nearly the speed of light in two opposite directions, so-called relativistic jets. These jets penetrate the outer layers of the dying star and race into space. When the particles in these jets collide with each other and with the surrounding material, the intense gamma rays are produced. The BOTE most likely belong to this category. Short gamma-ray bursts, less than 2 seconds, have a different origin. The collision of two extremely dense objects, such as neutron stars or a neutron star with a black hole. When these cosmic heavyweights merge, they release not only gamma rays, but also gravitational waves, vibrations of space-time itself, which are now directly measurable. But which of the two types could pose a danger to us? The short answer? Both. Both types of gamma-ray bursts could theoretically represent an existential threat to life on Earth. However, they differ considerably in their potential danger. Long gamma-ray bursts pose a significantly greater potential threat to us. The reason is simple. They are more frequent and more energetic. These bursts continuously release extreme amounts of radiation over extended periods, often 20 to 30 seconds, sometimes even several minutes. The total energy radiated is colossal, enough to endanger life on a planet thousands of light-years away. The real problem is not just the intensity, but also the frequency of such events. While massive stars that end in long GRBs are rare, they exist in sufficient numbers in our galaxy and its neighbouring galaxies. Astronomers have identified several star candidates that could potentially become hypernovae and produce long gamma-ray bursts. For example, Eta Carina, only about 7,500 light-years away, or WR104, at a distance of around 8,000 light-years. The critical question is always, does the star's rotational axis point in our direction? Because the jets are ejected along this axis. In the case of WR104, there is scientific debate about whether its poles might be aligned towards Earth. However, recent observations suggest that we are likely outside the danger zone. Short gamma-ray bursts are also extremely energetic, but they pose a lesser threat for several reasons. First, they last only fractions of a second to a maximum of 2 seconds, so the exposure time would be significantly shorter. Second, neutron star mergers are extremely rare in our immediate cosmic neighbourhood. The probability of two neutron stars merging dangerously close to Earth with a jet directed at us is practically zero. Neutron stars themselves are already the end product of stellar explosions and relatively stable objects. It often takes billions of years for two of them to get close enough to merge. While there are several known binary neutron star systems in our galactic neighborhood, none of them are close enough, nor are they expected to merge in the foreseeable future, astronomically speaking, to pose a threat. So what exactly would happen to us? If a gamma-ray burst were to hit Earth directly from close range, say, within 6,000 light-years, the result would be a mass extinction of unimaginable proportions. Death wouldn't be instantaneous, but would unfold over weeks, months, and years. A slow extinction of life on our planet. If the gamma-ray burst were to hit Earth, most people wouldn't notice anything at first. Gamma rays are invisible, odorless, and silent. But in those first few seconds, a catastrophe would already be set in motion. The high-energy radiation would strike the ozone layer at an altitude of 15 to 35 kilometers. That paper-thin layer that has protected us from the sun's deadly UV radiation for billions of years. Within seconds to minutes, the ozone layer would be decimated by 50% or more. Our planetary shield would be gone. And without the ozone layer, the full force of UV radiation would reach the Earth's surface. People outdoors would suffer severe burns within minutes. Within hours, unprotected eyes would be damaged by the UV radiation. Painful blindness would be the result. People would have to remain indoors permanently to survive. But the real catastrophe would unfold at the very foundation of life. Phytoplankton, microscopic algae on the surface of the oceans, produces about 50 to 80% of the oxygen in our atmosphere and is the first pillar of the marine food chain. These tiny organisms are extremely sensitive to UV radiation. Without ozone protection, phytoplankton would die off en masse. Within weeks, the entire marine food chain would collapse. Zooplankton would starve, followed by small fish, larger fish, marine mammals, and seabirds. The oceans would become dead zones. On land, plants would suffer from the UV radiation. Harvests would fail. Forests would die. Even if the ozone layer slowly recovers, a process that could take decades, the damage would already be done. Species that have survived for millions of years would be extinct. The oceans would be largely lifeless. The surface would be a hostile desert during the day. In the long term, oxygen production would also suffer, as most photosynthetic organisms would be destroyed. This exact scenario may have already occurred. Around 450 million years ago, at the end of the Ordovician period, approximately 85% of all species disappeared. Some scientists suspect that a gamma-ray burst could have destroyed the ozone layer, thus triggering this mass extinction. A nearby gamma-ray burst would not be a spectacular incineration in a fireball, but rather the silent, merciless annihilation of the foundations of life. A cosmic accident triggered by a dying star thousands of light years away would be enough to wipe out billions of years of evolution in weeks and months. This is the terrifying power of gamma-ray bursts, and the reason why we can only hope that the cosmic lottery continues to spare us. But how likely is it that this will actually happen to us? The good news first. The probability of a life-threatening gamma-ray burst hitting Earth is extremely low. However, it's not zero. For a gamma-ray burst to become an existential threat, several highly improbable factors must coincide. First, a massive star must explode, or two neutron stars must merge, and this must happen in our immediate cosmic neighborhood, within about 6,000 to 8,000 light-years. That sounds like a lot of space, but on the scale of our galaxy, which spans about 100,000 light-years, it's practically next door. Second, and this is crucial, one of the two jets produced in a GRB must be precisely aimed at Earth. These jets are extremely narrow, only a few degrees wide. The chance of us being caught in their path is therefore vanishingly small, less than 0.05%. Thirdly, this event must occur in the astronomical present, that is, within a time frame relevant to us humans. Scientists estimate that, statistically speaking, a truly dangerous gamma-ray burst could only hit Earth about every few 100 million years. Another reason to be reassured. Astronomers are closely monitoring known star candidates in our neighborhood. They know which massive stars could potentially end up in gamma-ray bursts. The most well-known candidate is Eta Carina, about 7,500 light-years away, one of the most massive stars in our galaxy. It is unstable and could theoretically explode at any time. However, observations indicate that its rotational axis does not point toward Earth. Even if it were to explode, we would likely only see a spectacular new star in the sky, but would not be exposed to a deadly gamma ray. Another candidate is WR104, about 8,000 light-years away. There was some concern about this star for a while, because early observations suggested its poles might point toward Earth. However, more recent, precise measurements have shown that we are most likely outside the danger zone. Its rotational axis is offset by about 30 to 40 degrees. The reassuring thing is, we wouldn't be completely surprised. Before a massive star explodes in a long gamma-ray burst, it typically shows signs of instability for decades or even centuries. Astronomers could detect such warning signals: increased brightness fluctuations, mass ejections, spectroscopic changes. However, and this is the uncomfortable truth, even if we were to detect an impending GRB decades in advance, there would be nothing we could do about it. There is no technology that could protect us from gamma radiation from space. We could, at best, prepare. Build underground bunkers, stockpile long-term supplies, construct greenhouses with UV filters. But that would be, at best, a survival strategy for a small number of people, not for the entire civilization. A nearby gamma-ray burst could wipe us out. Yes, it is a real, physically possible threat. But the probability of it happening in the foreseeable future, or indeed in the entire remaining lifespan of humanity, is vanishingly small. Statistically speaking, we should be more worried about asteroid impacts, which occur far more frequently. Gamma-ray bursts, on the other hand, are the cosmic version of a lightning strike. Theoretically lethal, but so improbable that there's no point in worrying about them constantly. We live in a quiet, relatively safe corner of the Milky Way, far from the massive, short-lived stars that could trigger GRBs. BOTE has reminded us how powerful and energetic the universe is, but it has also shown us how lucky we are. We live on a small blue planet that has so far been spared most cosmic catastrophes, and with a bit of luck, it will stay that way, at least for the next few 100 million years. If you enjoyed the video, I would really appreciate your support. I hope to see you next time.